Hi everyone, I'm Jim White. In the first part of this series, we talked primarily about relative humidity. In this second video, we're going to talk mostly about absolute humidity. And it's hard to talk about one without referring to the other. Now you'll get the most out of this video if you download the Humidity Moisture Handbook that I talked about in the Part 1 video. And I'll leave a link to that below. So we'll be referring to this as we go. Plus there's information in here that we're not going to cover in the video. So I recommend, if you have a serious interest in absolute humidity, that you download and print out a copy of this moisture handbook. In the Part 1 video, we showed this equation for relative humidity, where P sub W is the partial pressure of the water vapor, and we used P sub S for saturation, but the vapor pressure of water, P sub V, is essentially the same thing. And that ratio times 100 is a percent relative humidity. Now, one of the absolute moisture scales that we showed was the percent moisture by volume. And to me, this is the most intuitive of these scales. Again, just as we say in the atmosphere we have 20% oxygen, we can talk about the percent of moisture. And typically in a room where it is somewhat controlled temperature and humidity, you have about 1% moisture by volume. So this scale for absolute humidity, again, we have the partial pressure of the water vapor. And in this case, we talk about the total pressure, the total atmospheric pressure in the room, or in an industrial process. The pressure could be considerably different than normal atmospheric pressure. So that ratio times 100 is the percent moisture by volume. So you can see the equations are very similar. Now, an interesting thing to note is the vapor pressure of water is a function of temperature. And if we plot that, it looks something like this. So to come up with the percent relative humidity this way, you have to know the temperature. So you can measure the partial pressure of the water vapor, and you can derive the vapor pressure of the water by knowing the temperature. Now over here, temperature is not involved. So if we know the partial pressure of the water vapor and the total pressure, which is typically atmospheric pressure, you can come up with the percent moisture by volume totally independent of temperature. Now in the first video, we did a demonstration of measuring the vapor pressure of water using a sealed glass jar and some manometers. And first we took a sealed jar and went over to a pressure measuring device, and then we squirted some water into the jar. And when we started, the jar originally was open to atmosphere, so it already had some water vapor in the jar. Now, after we put in some water, by the way, everything was at the same temperature. So after we squirted water into the jar, the pressure went up. Now, if we did an accurate measurement of how much the pressure went up, and knowing the vapor pressure of water, we could have calculated the relative humidity in the jar before we started. Also, if in the case where we totally dried out the jar using the desiccant, we made sure we had totally dry air in the jar and then squirted in water, and the measured pressure went higher. And in this case, we could actually measure the temperature. If we had a chart of water vapor pressure versus temperature and measured this pressure, we could figure out what the temperature was. So this would be a side benefit of the experiment that we did. In the moisture handbook, one of the most useful and informative parts of it is this table in the back, which shows various moisture scales and the dew point temperature for which things were calculated. So I'm going to go to the computer now and talk more about what is available here in terms of data. Okay, here we are at the Mac Instruments website, and let's click on the handbook. And then over here is the PDF format. And let's scroll through till we come to the table. Okay. In the first column here, we have percent moisture by volume, and that's calculated for the dew point temperatures shown here. And everything here is calculated based on a pressure of 1 standard atmosphere. Okay, this column here is humidity ratio. Which is pounds of water vapor per pound of dry air. And that can be calculated directly from the moisture by volume. And that's shown in the handbook how to do that. And the same here for the specific humidity and the grams per cubic meter. Now let's go okay, here's a point resembling a possible room temperature. And what this is telling us is that at a dew point temperature of 76 Fahrenheit, we will have a moisture by volume of 3%. And you can interpolate between temperatures if you wanted to find the maximum moisture by volume at 72 degrees. You could do an interpolation between those two temperatures. So this is really the maximum moisture by volume that you can have at 76 degrees Fahrenheit. So that would be 100% relative humidity. Now if you happen to have a 50% relative humidity in a room that's at 76 degrees Fahrenheit, you would have half that amount of moisture by volume, or it would be 1.5% moisture by volume. So another thing we can get from this table is the vapor pressure of water vapor at this temperature. Since everything here is calculated at 1 atmosphere, this is telling us we have 3% of 1 atmosphere at this temperature. So that's the vapor pressure, 3% of 1 atmosphere. So you can go here to any temperature, and this is telling you what the water vapor pressure will be as a percentage of total pressure at that temperature. So there's quite a lot of information embedded in this table that you can look at it in various ways. And a lot of this is explained in the text of the handbook itself. But this table is very useful, and it goes on up to the boiling point of water. If I can get there. So here's 100 degrees C. We can have 100% moisture by volume. And here we can see where the humidity ratio scale is not very nice at high values of moisture because it goes to infinity. Now the grams of moisture per cubic meter, which some people call the absolute humidity, is a very cumbersome thing to me, at any rate. Everything here is reflected to a standard temperature and pressure, and that's as defined by the International Union of Pure and Applied Chemistry, which is 1 atmosphere and 0 degrees C. So we know we can't have more than 0.6% moisture by volume at 0 degrees C. If I can get to the beginning of the table. Here we are, 0 degrees C. The maximum moisture by volume that you can have is 0.6%. So these numbers are all calculated based on that, and it just doesn't give you an intuitive feel for anything. I can double the pressure of air at any given moisture by volume. Let's say we are at 1% moisture by volume and doubled the pressure. We would still have 1% moisture by volume. But over here, we'd have the same amount of moisture compressed to half the volume, so this number would double. So it's very hard to use and very non-intuitive. So percent moisture by volume is intuitive and tells you what's going on. And I think it's more absolute because you can heat the air, cool it, compress it, and the percent moisture by volume stays the same as long as you don't go below the dew point temperature. So there's a lot of information in this table. So I hope you'll look at it and get a feel for what's going on here. Well, I apologize for that. The screen recording software does not keep up with the cursor very well. So I hope you were able to follow through the words that I was speaking. So as we just showed, that table can be used in a lot of different ways. And let me show you a typical calculation of something that you might be interested in that has to do with absolute and relative humidity. I'm standing in a room that is approximately 16 feet by 22 feet by 8 feet in dimension. And we might wonder, well, how much water vapor is in a room like this? And this turns out to be about 2,800 cubic feet, which is about 79 cubic meters in volume. And the temperature in here is 72 degrees Fahrenheit. Now, from that table in the moisture handbook, you can do an interpolation to find out the maximum moisture by volume at 72 degrees. And that turns out to be 2.66%. So at 100% relative humidity, at this temperature, we can have 2.66% moisture by volume. Now, actually, we keep the room here at about a 50% relative humidity, and so our moisture by volume is really 1.33%. So the density of air at this temperature is 1.2 kilograms per cubic meter, and for the 78.8 cubic meters times that density, we end up with 95 kilograms of air in this room. That's 209 pounds. Although you can't see it and you can barely feel it, there's a considerable weight of air in a room. Now, if 1.33% of that is water vapor, we take the cubic meters times 0.0133, and there's a little more than a cubic meter of water vapor in the room. And from the part 1 video, we know that water vapor is only 62% as heavy as dry air. So if we take our 1.05 cubic meters times the density of water vapor, we end up with 0.79 kilograms. So there's almost 0.8 liters of water in this room. And if we were at 100% RH, that would almost be 1.6 liters. So again, it's kind of astounding when you go through the calculations and see the reality of weights and volumes. So I hope you got something out of this video, or the 2 videos, and I hope you have a better understanding of both relative humidity and absolute humidity. So I hope to see you in the next video.